Welcome to the Futurist Society podcast, where we delve into the latest advancements in technology, science, and culture. From discussions on the latest breakthroughs in AI, biotechnology, and space exploration, the Futurist Society is your window into all of the awesomeness that the future holds. Get ready to be informed and inspired as we consider the positive impact of emerging technologies on humanity. Without further ado, welcome your host, Dr. Awesome.
Hey, everybody. Welcome back to the Futurist Society, where, as always, we are talking in the present, but talking about the future. I have with me today Dr. David Rosen, who's a professor at Northeastern University in the Department of Electrical Engineering and Mathematics. And more importantly, he is doing a lot of really interesting and amazing things in the fields of artificial intelligence, robots, machine learning. And I think that's really on everybody's mind right now. But most specifically, I wanted to talk with him about a program that he's heading up called Neural, which is doing really cool stuff in robotics. So tell us a little bit about Neural, about how you got into the position you are, because I think you started out in math for a little bit and now are doing a lot of cool stuff with robotics. But let's learn a little bit about what Neural is doing for us.
Okay, cool. Well, yeah, thanks very much for the invitation. So Neural is the Northeastern University Robust Autonomy Laboratory, which is the research group that I run. And the motivation for this is, if you think about the kinds of robots that we want to have in the future, right? These are going to be things that are operating ubiquitously in society, like out of the lab, in the world, doing useful stuff. And if you think about a lot of the areas where there's the most potential for autonomous systems to do the most good, a lot of these areas are characterized by having robots that are controlling, potentially dangerous or expensive pieces of machinery, things like autonomous vehicles or aviation, or robots in the home that are operating potentially in close proximity to people. Mm-hmm. And so the areas that are sort of the most high impact ones that we'd like to target for these autonomous systems also happen to be areas where, because of the nature of the work involved, making poor decisions can be really costly. Mm-hmm. And so the real goal of my research group is to try to figure out how we can design perception, planning, and control systems for autonomous systems that can achieve a level of safety and reliability that would make the deployment of these autonomous systems in the really high impact, but also safety critical applications socially acceptable.
Yeah, I think that safety is on everybody's mind when they're thinking about giving up some sort of control to a robot or some sort of algorithm, especially when it comes to things that are around humans, like full self-driving cars or consumer robots. So what are the strides that you guys have made right now that might be something that people are looking at?
Okay, yeah. So maybe by way of answering that question, I might perhaps start by saying maybe how our approach to research differs a little bit from how a lot of robotics or AI work is commonly done, mm-hmm. sort of what we're adding to the discussion. Mm-hmm. So the sort of, as you mentioned, my background actually is in mathematics. And so that's kind of the lens that we adopt when we're looking at problems in autonomy. And from that perspective, sort of the core technology that we use, or that is the basis for a lot of our work, is really optimization. Mm-hmm. Because if you think about, we want to have an artificially intelligent agent, what does that really mean? Well, roughly speaking, what that means is you want to have an agent that understands how to take the best course of action in a given set of circumstances. Mm-hmm. And that could be, finding the shortest path, or minimizing, costs, things of that sort. But anytime you're talking about making a decision where you're talking about superlatives, best, fastest, et cetera, what you're really describing is an optimization problem of a sort. And mm-hmm. so what this means then is, basically every problem in artificial intelligence can be pretty naturally formulated as an optimization problem. Mm-hmm. And from the engineering standpoint, most of the engineering knowledge goes into the formulation of what that problem is supposed to look like. So, mm-hmm. If I'm trying to build an autonomous car, I would expect that, variables like fuel and, speed and things of that sort should somehow appear in the decisions that this thing is making. But that's really just a description of what the problem is. Mm-hmm. Once you kind of boiled it down to the description of the problem that you're trying to solve, the next question then is, how do you actually do that solving? Mm-hmm. And that's essentially a mathematical question. Mm-hmm. Maybe the interesting bit where our work starts to come in is that if you look at the properties that these optimization problems have, especially ones that show up in what's called physically embodied AI, things like robotics or, well, mostly robotics, yeah, things that have to do with physical space. It turns out that a lot of those optimization problems are just fundamentally hard to solve in the sense of computational complexity theory. And that's a serious barrier to our ability to actually implement and deploy these systems. Because if you think about what a robot is going to look like, these tend to be very, very lightweight robotic platforms. They don't have a whole lot of compute. And not only that, but they also by nature have to operate in hard real time, controlling physical systems that have to make decisions extremely quickly. And so they don't have a whole lot of time to sit there and think about what they want to do next. They have to make decisions right away. And so there's kind of a tension here then between, on the one hand, these things have to solve these problems that are just provably computationally hard. But on the other hand, they have to make decisions right now using very, very limited computational resources. And so in the past, the way that a lot of sort of classical robotic systems have been designed is just through the use of heuristics, meaning that somebody just says, okay, well, this is a hard problem. Let's just make up an approximation, like linearizing something or pretending that this is linear when it's actually not, or things of that sort. So that approach has gone a long way towards enabling us to build robots that are able to operate like at all. But the price that you pay for doing that is that it then becomes very, very hard to say under what conditions these things are gonna produce behaviors that look, for lack of a better description, sane. Because you basically just made a bunch of approximations. So it's not necessarily clear under what conditions these are going to work well, or maybe even what the parameters are that would control the behavior of these downstream systems.
Yeah, I feel like that's such a complex problem. You know, I think that when you're talking about, from a layperson like myself, when you're talking about performance, I'm thinking like performing better for what purpose, right? Like if the purpose is to get to, you know, point A to point B fast enough, I'm sure there's a certain algorithm for that. But if the purpose is to get from point A to point B without hurting anybody, without having any sort of like, you know, negative situation that might impact a human from a harm perspective, I feel like that's a different algorithm. Like how are you guys able to juggle all of these different things? You know, like when I think about is like the train problem, right? Like your train is going down the road and you can either derail it and hurt one person, or you can let it go and then it hurts a lot of people, right? And so how do you make that into a mathematical algorithm that a computer can understand?
Yeah. So I should first by saying we're sort of looking at, I think, much lower level problems than sort of the moral reasoning problem that you're
Gotcha.
You could, in principle, come up with a solution to such a problem. The catch is that for the stuff that we do, we're primarily looking at how to solve a problem that's already presented to us.
Okay.
It's not 100% clear how you necessarily.
Yeah. So I guess moral reasoning is different from safety, but I just feel like they're so close, you know, I don't know. Maybe that's, again, as somebody who's not in the field, like I don't understand it as well as I should, but give me some examples of like safety stuff that would make people who are hesitant about robotics be a little bit more comfortable with the idea of it.
Sure. Yeah. So I can give you maybe some examples of some stuff we've worked in the past.
Yeah. Yeah.
So one of the areas we've spent a lot of time working on is robotic perception. So, you know, as I mentioned before, we do a lot of work in embodied AI.
Okay.
So, problems related to physically embodied agents. So unsurprisingly there, you know, geometry is really prominent there because the whole point of having a robot is that you can reach out and interact with physically. So if you think about a lot of the problems that you want robotics to be able to solve, all these things that involve like, you know, planning, perception, control, and navigation and stuff require that you have an accurate model of the environment so that you're not like, you know, driving into walls or things of that sort. So it turns out that this so-called spatial perception or mapping problem, that is, I just want to be able to collect data from onboard sensors and reconstruct a geometrically accurate model of the world, actually falls into this very, very difficult problem class that I mentioned before, where there are not fast general purpose algorithms for solving this. And so similar to kind of what I was mentioning before, prior to a lot of the work that my group has done, those problems would have been solved using heuristics. And so those heuristics...
Heuristics is just trial and error, correct? Like like, what do you mean by heuristic?
Sure, yeah, so I can make that a little bit more precise. So as I mentioned, these are formulated as optimization problems. The sharp distinction between what was done before and what we're doing was prior to our work, those were solved using local search. And so what that means is, you know, if you imagine an objective that describes how well a potential solution is doing, you should think of this as being, you know, I've got some large landscape of potential answers. And each of those points has like a cost associated with it, or a measure of goodness. And so conceptually, you can think of this as being like the topography of like a large mountain range. And so, you know, what local optimization attempts to do is you pick a starting point and you just try to improve it by locally sort of making small adjustments to it. So if you think of this sort of by this, you know, landscape analogy, effectively you're starting at some random spot in the mountain range and you're going downhill. And whatever local value you end up in is sort of where you end up. So that's local optimization. But what we want to do is global optimization, is we want to find the best answer, which is really the lowest point everywhere. And so similar to this mountain range analogy, if you're a hiker on one of these valleys and you're locally looking around, you actually have no idea where the actual answer is.
Right, right.
So roughly speaking, what was done in the past was primarily based on local optimization. And so oftentimes that works. And the advantage to that is that it can be done fast. Classic algorithms like gradient descent, which, if you study, let's say, machine learning or introductory optimization, sort of everybody knows, have the advantage that they can be run very, very fast. And so they're relatively lightweight. And so they're suitable for deployment on these lightweight mobile platforms. The catch is that you can't say anything about what you're going to get. And so it turns out that these spatial estimation problems have the property that if you find a local but not global minimum, it basically is just total nonsense. And so, if you think about what does that mean for safety and reliability, if you imagine that you're in your autonomous car and you're driving down the Autobahn at 90 miles an hour, and the map that you get that is telling you, where's the guardrail, where are other cars around me, looks like some crazy Inception-esque like hairball that you would find at the bottom of your shower drain, which is typically what they look like when they find the wrong answer. You can imagine you're gonna have a very bad day. And so a lot of the work that we've looked at then is, how can you take, how is it possible to solve these really complex optimization problems like that in a manner that is fast enough to be useful for these real-time systems, but that also lets you say something concrete about, or much stronger about, the quality of the solutions that you're gonna get out of that.
Yeah. So from what I'm hearing, and correct me if I'm wrong, is that a local system is just based around everything that's around you right then and there.
Yeah.
Whereas a more global system, you can draw on past experiences, on other information, just like having more data that's available to you. Similar to how a child might not remember yesterday that what their room looks like, but you and I could do it to the point where we can navigate our bedroom with our eyes closed, right? Is that what you're talking about?
I think,
or is it a little bit more complex than that?
Something like, going back to this sort of like landscape example, if you were to ask me like, what's the highest point around you that you can see right now? And, you might say something like in the city of Boston, maybe the top of the Hancock. That would be like a notion of local maximum. Whereas the global solution to this problem would be the top of Mount Everest, which is halfway around the world. So maybe one way of saying this is that the kinds of methods that are commonly used right now are limited by this notion of locality, that you're having to pick a starting point and then sort of make local adjustment or local improvements to your solution. Where these things fall down essentially is that it's not clear how the way to say it basically would be that, you can imagine that where you end up in an approach like that depends on where you start. If we're trying to find the tallest building locally, let's say in Boston, that might look like the Hancock Prudential Center. If you ask this question in Toronto, you might get the CN Tower or something like that. Whereas, if you're asking what is the globally highest point on Earth, there's only one, right? It's Mount Everest. And so that's where we want to end up always. We don't want to find these local suboptimal solutions. We want to find these global solutions. But you can probably tell from that analogy, that's a much harder problem. Right. Because you're talking about something which requires global knowledge of the state space.
Yeah.
Which is much, much harder.
Right, right. Yeah, I mean, I hear that a lot from, like, I just feel like the promise of robotics has been something that's always like 20 years away, and like you see cartoons like the Jetsons or, something like that. And this is just around the horizon. I mean, when Back to the Future went to the future, it was, 20 years ago when they went to the future, right? And they had automatic dog walkers and all this stuff. So I feel like the promise for the general public of robots is something that has been so ingrained in our psyche. And the more that I talk to people like yourself that are doing it on the ground level, I realize just like how much more complex it is and like how far we have to go. But then on the same token, I see, what is this robotics team that was like sorting different items based on just like a speech algorithm. It was like, separate out the apples, and it would separate out the apples. And it was like a humanoid robot or something like that. That's making the rounds of the internet. If you guys haven't seen it, go check it out. But, or like, you see like Atlas Robotics is like, creating a whole bunch of humanoid robots that can traverse all these different environments, or, I feel like there's a discrepancy between like what I see that's technologically available versus when I talk to you to someone like you, and there's like this idea of complexity that I feel like is almost insurmountable. So like, how does, like, where do you see it from your standpoint? You're on the bleeding edge of robotics. Like, do you feel like this stuff is going to be there within our lifetimes? And if so, like, is it something that we can trust reliably around our kids and, make sure that that's something that's safe enough for all of us? Like, how do you see it?
Yeah, so I think the issue that you mentioned is really exactly the motivation behind a lot of the work that we're doing, which is this idea that, a lot of these robots that are built on sort of these more heuristic techniques. And so, that's very encouraging in the sense that we can demonstrate at least the inklings of these kinds of capabilities that we would want to have. But when you say, as you point out, like, okay, that's great, but like, why don't these things exist out in the world then, right? Oftentimes what you find is that you get these very, very long tail effects, right? Where, which kind of goes back to, I think, what I was mentioning at the opening, which was that, when you consider if these things really were to be out of the lab, operating in the real world, just the scale of that deployment is so vast that, even these really, really long tail corner cases are going to
be a problem.
They're going to be a problem.
Yeah.
And when you're talking about, the control of safety critical systems or life critical systems,
right?
Like,
you can't have that high chance.
And so, I think what a lot of roboticists, and certainly myself, believe is that it's these really long tail sort of rare failure modes, rare but pernicious failure modes, that really are the limitation that prevents us from having that kind of ubiquitous, like Jetsons-like deployment right now. And so the motivation behind a lot of this optimization work that we've been doing, in this more computational complexity or like theoretical computer science type work, is to produce the decision-making control algorithms that don't suffer from those long tail failures. And so in particular, the stuff that the main distinction between like our approach versus what we've done in the past is that we can actually prove that we're going to get the right answer, at least under certain cases. And not only that, but when we get a solution from one of these methods, we don't just get a solution, but we get what's called a computational certificate of correctness. Meaning not only do I have the answer, but I know that I have the right answer and I can actually prove it to somebody else. And so, if we go back to our autonomous driving scenario, the distinction between there is like, with an existing sort of approach that's based on these heuristics, if an autonomous car gets the wrong answer, it doesn't even know that it has the wrong answer. And so it will happily execute, a path that was planned against a map that is nonsense and like drive off the bridge. Whereas using these certifiable techniques, it may occasionally get a wrong answer under very adverse circumstances, but it will be able to recognize that is the case, or it will be able to recognize that it's approaching an area of operation that's unsafe.
Interesting.
And at that point, it can proactively do something like, ask a human for help or something like that before it makes a terrible decision.
Yeah.
So
it's almost like what they talk about with artificial general intelligence, like the idea to have not only just reason, but also judgment, right?
Exactly. Yeah. So the term that we've started to kind of use around this is we at least my group refers to this as the ability to do introspective autonomy. Right? So to actually understand that you've got the right answer, or you don't have the right answer, or to recognize when you might be about to make a mistake.
Interesting. Wow. So like I hear that, and that's awesome that you're doing that. I think that that's something that's going to be really interesting to see. I feel like we're in the first little baby steps of artificial general intelligence. Who do you think is doing it the best? Is it academics, like what you're doing in your lab, or is it private industry?
That's a very broad question.
Yeah.
I'm going to answer this.
Here's the reason why I think that I like your approach is, first off, because of the democratization, right? Like if you create this free model that everybody else is allowed to use, then a young kid that is interested in making some sort of, in-the-house robot might have the ability to catch up with some of these larger companies that, from everything you're saying, it seems like the moat is so complex that like nobody's ever going to be able to overcome that, and if that happens, then it's going to be decades before it actually gets into our houses. Am I wrong in that?
Yeah, maybe the way that I would answer this is, I would say that academia and industry have complementary roles to play. I would say that they're better at doing different kinds of things.
Yeah.
So things that the industry is really going to excel at are things that require just having the scope and scale that industry can provide in terms of manpower, data collection, resources, and so on.
Just really get it done faster, probably too.
Yeah, or training these super large machine learning, like that's what they call them, foundation models that are built on just incredible amounts of data, like hoovering up large fractions of the internet and so on. That's just, logistically way beyond the capabilities that academic research organizations have. And so that's great that they can do that. And, what we've seen recently with, large language models and so on is that just the benefits of having extremely large corpuses of data sets like that can enable you to do amazing things. But, that's one aspect of what it means to build intelligent agents. one of the things that I'm a little apprehensive about, which again is kind of the motivation behind our work, is, like LLMs can do seemingly incredible things, but they also are well known to be susceptible to these hallucination effects, which I think of again as being another instance of safety and reliability.
Yeah.
So private industry can produce these incredible, large foundation models. But if you're going to ask somebody, okay, I'm going to put you inside an aircraft that is being driven by one of these models that is totally black box,
right?
Like, would you feel comfortable getting onto a flight like that? I personally wouldn't.
Yeah.
So I think where academia can have like a big role to play is really not necessarily, we're not going to be able to compete in terms of scope and scale. But I think there's definitely a lot of like very fundamental scientific questions that need to be addressed in order to understand how these systems work and how to make them safe and reliable that actually don't require these very large resources to be able to answer. So that's the kind of stuff in my group trying to answer right now.
Yeah, no, that's really, really interesting. Do you follow science fiction? Are you a fan? What is like the artificial intelligence model that you think is like the most benign? Like what are you trying to achieve? Like, because I look at like Isaac Asimov wrote some of like the seminal works, and like I look at like his 3 laws, and I thought that was so profound, and I'm sure there must be a certain amount of elegance to the math that you're making, right? And that must be, coming from somewhere. Like, what is the promise road that you're trying to achieve?
Okay, yeah. So maybe there's 2 answers that I can give to that question. So in terms of like, is there a particular character in like sci-fi that I especially identify with in terms of what we're trying to do? I grew up watching a lot of Star Trek.
Yeah, me too. Yeah.
So I would definitely say that Commander Data is like.
Yeah, he's like absolutely like one of the best characters.
He's the best.
His whole grappling with like what it means to be human was, I thought, the best out of all the Star Trek like mega plots, right? Like just like there's so many different things, but I mean, he like, that's an artificial intelligence that has reason very similar to what a human is at right now, right? Like we're a long way away from that. But is there anything like that you're looking at as like, okay, if we can achieve this, then like that would be good for humanity today?
Oh, well, yeah. So, I think, like I said, the real motivation behind a lot of our stuff is that we want to get these devices out in the world doing useful stuff. And especially, the ability to design autonomous systems that can guarantee safety would have tremendous social impact. So just to take one example, one of the reasons one of the motivations or application areas that we're especially excited about is autonomous driving. And, just to give some concrete numbers, the last time I looked at this, the NTHSB tracks this stuff all the time. And I think the last report that I read from them indicates that there's about 40,000 fatal car accidents every year. And if you look at like accident investigations as to, what is actually the cause of this, right? Unsurprisingly, it's predominantly people just doing super dumb stuff. Right? And like, driving drunk, driving tired.
Texting while driving.
Not paying attention.
Yeah.
Well, okay, robots don't get distracted. We're drunk, we're tired. And so, one of the things that we're very interested in applying some of this technology to in the near term are things like active driver safety assistance systems. So imagine having a vehicle that is built on top of these algorithms that deeply understands the underlying physical model and knows how to take appropriate and provably safe actions given those models. And as a result is effectively not crashing. Right? At least up to the limits of physics. So you're no longer limited by driver skill or lack thereof. You're just now limited by the physical capabilities of the underlying vehicle. So if it is possible to avoid an accident, this thing will find a way to do it. And not only that, but because these things are software is infinitely replicable. Training a professional driver right now is done one at a time, right? In a large scale deployment like what we were discussing here, right? As soon as one car learns how to do something, all the cars know how to do it. Right? So these things are going to be continuously improving over time. And that's just sort of one example, but there's also applications in terms of our ability to actually use robots as scientific instruments, in fact. So one of the reasons that I was excited to come to Northeastern is that Northeastern has a very active field robotics program. And a lot of the work that we do is actually targeted at scientific applications, especially like oceanic and environmental monitoring for climate change mitigation. And so again, similar thing there, just the spatial and temporal scales that you would have to be able to do environmental monitoring at in order to get the data that is needed to answer these really pressing societal questions just necessitates the use of automation at very, very large scales. And so again, how do you deploy large numbers of autonomous systems like that are going to do the right thing, that are smart enough to understand, what they need to do where in order to get the data that is of scientific interest and so on. It's very much an open problem, but looks exactly like the sort of problem that is amenable to the kind of techniques that we're hoping to develop.
Okay. I just want to double click on the full self-driving component for just a second, because I feel like First off, Tesla just released their full self-driving beta. What do you think about that? Like, what are your thoughts on that?
Okay, well, at the risk of potentially, hopefully not alienating some of your viewers, I honestly take kind of a dim view of Tesla's approach to this.
Yeah, because it's the heuristic model, right?
Yeah, I mean, effectively what Tesla was doing is they were running a gigantic unsanctioned human subject experiment on everybody who's on the road that I certainly never signed up for. And I'm not a huge fan of. And so I mean, even calling it full self-driving is, I think, both intentionally misleading and therefore I would say unethical. I mean, if you read the fine print, it is absolutely not. Number one. Number two, I think calling it that is a marketing gimmick. But I think it lulls people into a false sense of security because, you know, folks who maybe are not experts don't realize the limitations of these existing systems and the fact that they are not simply reliable.
Yeah. What about the auto taxis that are in Arizona? These, I forgot the name of them, but like they pick you up from the Tucson airport and then they take you to your hotel. Have you seen that at all?
I've seen it. Yeah. I mean,
is that just because it's like a fixed road and it's basically like driving by rail, or like who's closest to that? Number one.
So, okay, I should probably preface this by saying that I'm a little biased because I used to work with them.
Oh, okay.
But
okay.
I actually like Google's approach to this.
Yeah.
In part because they are, I think, being much more cautious and honest in both what they're attempting to achieve in the short term and in the claims that they're making about what their capabilities are. I think that they're pursuing. I think that they are doing a little bit of a better job about pursuing a more methodical scientific approach, not trying to go too far too fast and thereby endangering people that are using it.
What are they claiming that's different from Tesla? Like, as somebody that's not following it, you know, on a day-to-day basis, I mean, this is something that's you're very close to. Like, how is someone like me that's not involved in your field able to differentiate between one full self-driving versus another?
Well, I don't know of anybody that actually has what I would call full self-driving right now. And again, it's because of these very difficult sort of long tail. So, you know, most driving is not that interesting in the sense that, as you say, you know, like you're on the road and you're driving forward and you're in the lanes and it's fine. But what makes driving difficult is the fact that occasionally weird stuff happens and you have to not, you know, crash your car with those.
Right.
So things like, you know, like entering a construction zone, for instance, right? You know, there's road work being done and there's lane shifts that happen with cones and so on. You know, you're having to adapt to an unforeseen circumstance that may not look like anything you've seen in that area before because it's new. Right? And so your ability to understand how to make the correct decision when you are confronted with novel scenarios is the sort of thing that principal reasoning algorithms do much better than sort of, I don't want to paint with too broad, but the whole idea of machine learning is basically that you were going to have a data set that is representative of what you're going to see in the future. And so, you know, it's great when you can do that. But one of the big problems in machine learning writ large is what they call domain shift, where suddenly something in the world changes and your training data that your system is trained on is no longer representative of what you're seeing now. And so things like, you know, unexpected changes in the environment are the sort of things that happen all the time in you know, let's say driving scenarios that some of these classical ways of building the systems may not handle especially well. Yeah. And not only may they not handle it especially well, but kind of as I was alluding to before, they may not even realize that they're not handling it, which is when you can really get yourself in trouble.
So is it really only going to be safe when we have artificial intelligence similar to, I mean, obviously not like commander data, but, you know, something a couple shades below that, you know, such that it can identify things like a human? Like, are we close enough to that such that it will be within our lifetimes, or are we going to continually wait for artificial intelligence to be as close to us as possible before you think it's going to be accepted by everyone?
Okay. Yeah, I would say in terms of social acceptance and broad scale deployment of that sort, the thing that I'm really aiming at is I want to get away from AI as a black box that you just have to hope is going to do the right thing. Maybe that's the way to say it. I mean, if I were going to draw an honest block diagram for most existing robotics or AI systems, there would be a giant box in the middle of that diagram that's just labeled hope, right? And I find that very unsatisfying. So what we are attempting to do really is to take the guesswork out of this. Right? We want to produce methods that you don't have to just take trust on faith, but that are correct by construction, that actually are provably going to do the right thing, at least within a restricted regime of operation that you can quantify so that you know if you're about to enter an unsafe state. So we're looking at that from the perspective of optimization techniques, but similar kinds of approaches can be applied actually to machine learning systems as well, which is another area that we're very interested in. So, for example, you know, if you train some deep net model, how do you know that this is going to do the right thing presented with data of a certain type? Let's say, can you say anything about the reliability of that system. Can you do verification is what it's often used to describe this. And so we're one of the applications that we're very interested in applying some of the technology that we're developing too is verification of learned perceptual models and learned controllers as well. So being able to say that, like, at least within the following set of circumstances, I can guarantee that this even learned model is gonna operate safely.
That's awesome, man. I mean, I can see what it is that you're talking about. I just always want this thing to happen very soon, and I feel like, you know, the more that you talk about it, the more I realize that, like, you know, it's not as close as I once thought it was, right? I mean, maybe, you know, Tesla or Google or somebody will put out something that is a heuristic model that the risk of, you know, something adverse happening is so incredibly low that they feel comfortable putting it out there. But the way that you're talking about it seems like the most logical way to go about it is to have maybe some sort of judgment that the computer has, as opposed to just following a set of orders because of trial and error from an algorithm that you don't have any access to, right? Like, you don't have the ability to look at it. So I don't know. I mean, you're on the cutting edge. How far away do you feel like we are away from this stuff?
Well, I mean, you know, the pithy remarks that predicting the future is hard.
Yeah.
So I hesitate to make any concrete predictions about this, in part because actually that space that I'm describing now is actually evolving really, really fast, which is actually I've been very, very excited about. So the algorithms of the sort that I was describing didn't actually exist even like 5 or 7 years ago. Like, that's about when these things started to emerge on the scene, at least in the context of robotics anyway. And there's been a tremendous development in that space over the last 5 or 7 years. And I think we really kind of have hit an inflection point with respect to those kind of certifiable or verifiable systems in the past, even just 2 or 3 years, in terms of, you know, the number of people that are now, number one, kind of excited about this, and number two, really devoting a lot of really serious research effort to it. So I mean, I'm a little bit of an optimist myself in terms of that sense. So I actually don't think it would be unreasonable to predict that we might start to see a lot of these sort of you know, verifiable systems coming out in the next, you know, 5 years or so. Not that far off.
So there's a component of the car itself being smart and smart enough to navigate all of these edge cases. But there's also from what I understand, is there's the idea of the cars talking to each other also to make sure that en masse they're able to predict any sort of strategic error from happening that would harm somebody. Is that something that's also being pursued at the level that, you know, you're at? Like, I feel like when I for example, like when I watch iRobot, there's everything is going in one path. Everything is going in, like, it's almost like an artery where all the blood vessels are lining up in the same way, right? Is that something that all these different companies are looking into, or is that something that's probably going to be a lot more difficult, just considering the fact that there's different companies involved?
Oh yeah, so I mean, certainly within a company, like companies are definitely aware that, you know, the ability to sort of coordinate the actions of multiple autonomous systems is hugely beneficial. Information sharing. Fleets of autonomous vehicles is a good example of this because, you know, as I mentioned, sort of construction zones earlier. You could imagine that one car says, "Oh yeah, it turns out, you know, there's construction on Broadway now. You know, we use motor cars to know that when we're doing route planning and so on." So that's definitely something that is of interest and is being actively worked on. Interestingly enough, I mean, it turns out you can cast that problem in the same sort of optimization-based framework that we were discussing before. The catch now is that, you know, you have to worry about not just, you know, can you solve this problem in the abstract, but now you also have to worry about things like communication constraints and data locality, because not all your agents may have access to the same data at the same time. And, you know, at least if you're talking about deployments of mobile devices that may or may not be in, you know, Wi-Fi range, it may be that, you know, they only have the ability to send messages infrequently, and those messages may have to be small because they're being transmitted via satellite or cell phones and stuff. And so it actually can be cast as the same problem, but now with a much more sort of operational constraints around communication and data transfer and locality and so on.
One of the things that you had mentioned when we were talking before we started the podcast is there's some certain fundamental principles that someone like yourself would want to know to get into this field, because I feel like it's such an interesting field. You're saying there's a lot more investment and interest in robotics in general, which is something that I definitely see. Like, there's more newspaper articles about it, more people who are not in the field are talking about it. If somebody was like a young kid that wanted to get into just the ideas that you're presenting here, I think you had said, like, data theory was one of them, like linear algebra. What are the fundamentals that kids should learn?
Okay, yeah. So I can speak maybe sort of in a broad, high level first, and then maybe a little more specifically about some of our stuff.
Yeah.
So, I mean, for anybody who's listening who wants to get into like scientific computation or anything to do with computing on data at all, like you gotta know linear algebra. Linear algebra is absolutely the foundation of all scientific computation, and numerical linear algebra in particular. And I always want to call that out because there's linear algebra that you might study at the level of like an undergraduate, which is all about like linear systems and how to solve linear equations and so on. It turns out that numerical linear algebra is really the study of, okay, I want to solve a linear system, but I want to actually do this using computers which have finite memory, and where computation time in terms of number of operations is also the consideration, because we want to do stuff fast. And so linear algebra is really the study of not just linear algebra, but specifically how do you implement linear algebra operations on finite memory computers. And so that's like a whole nother deeper level of study, but that's like absolutely the foundation of like pretty much all of applied mathematics is really just a giant machine for taking broad classes of problems and reducing them to sequences of linear algebra problems that are basically the only kinds of general problems that we really know how to solve. So that's definitely the foundation. And then, if you want to get more into like data science or AI type stuff, kind of as I mentioned before, most of the problems that you're going to be tackling, whether it be training neural networks or trying to come up with algorithms that make good decisions and so on, all these problems can be formulated as optimization problems. And so really the core of almost all scientific computation is a combination of numerical linear algebra and optimization.
Interesting. Yeah, no, I just feel like, if even for someone like myself to understand what is the basis for how these things are working, it would give me some sort of idea for when I would feel comfortable with bringing them into like my household. Like if, for example, like a consumer robot that would able to fold my laundry. Like I want to know where are we at with that so that it's safe enough to have around my kids, right? And just maybe, I don't know, like learning a little bit of kind of like where we were at with the topics that you mentioned. Maybe somebody that might be interested might be able to make the decision a little bit better. But I feel like those are two different things. Like what you're talking about is like the actual nuts and bolts of how you're building it. Is there any value in learning them just as like a layperson when we're talking about some of these more general concepts?
Oh, I think totally. Yeah. I mean, like one of the things I tell my students is that like, you can never overinvest in the fundamentals. Right? And like when people ask me, okay, like suppose that I study math, what can I do with that? Usually the answer that I give is like literally whatever you want.
Yeah.
And
that's what I heard too.
Maybe my own, maybe my personal life experience here is maybe
it's
like I didn't set out with the intention of becoming a roboticist.
Right.
Like, I actually began life originally as a physicist, I guess.
Okay.
Subsequently, I switched to math, but like I never set out with the intention of doing robotics. I kind of just fell into it as a hobby.
Right.
But I was very well positioned to do it when I actually decided to change my professional focus. Because what math really teaches you how to do is it teaches you how to think rigorously, like to be able to understand, okay, when I'm looking at a problem, what is the structure of that problem that's important for understanding how to solve it? Like, how do I separate out the really core ideas involved in this problem from sort of the details that don't really matter that much? How do I take an ill-formed sort of natural language idea and sharpen it into a statement that is precise so that I can then make forward progress on it? And like, certainly when I've been recruiting both like in academia and even before, I did a couple of years in industry, when we were trying to hire people, that was like the number one skill that we were looking for is like, how can you make your ideas precise so that you can actually start to attack them in like a principled and deliberate way that enables you to make actual forward progress when trying to solve difficult technical problems.
Yeah, that's interesting and certainly important. I feel like, math is something that is the substructure of everything that we have, right? And so I could see somebody making a transition into another technical field, but specifically robotics. I think you had talked about you were doing first robotics competitions for a while and then made the transition because you enjoyed it so much. Is that?
Yeah, I started in high school. I just, as it turns out, I was a giant nerd. So, I had kind of taken like I think all the available AP classes by my senior year. So I had a free period.
Right.
And one of my buddies just said, "Hey, I'm starting this robotics team. Want to join?" I said, "Sure, it sounds fun."
Yeah.
And I just kind of kept doing that when I got to college, just as a hobby on the side with student groups and stuff. And kind of just kept doing it throughout college. And by the time I got into graduate school, what I realized was that, a lot of the math that I had been studying in quote unquote like my professional capacity during that time actually mapped really well onto a lot of the engineering and sort of physical problems that arise in robotics applications. And it turns out that a lot of traditional engineering programs, like mechanical engineering or electrical engineering, don't necessarily cover some of the mathematics that is really useful and kind of, I would say, really required for modeling robotic problems. So a good example of this would be something like, it turns out there are mathematical objects called manifolds that basically, you can think of as being smooth objects in a sense, right? So think of like a sphere. It turns out that kind of language, the language of smooth manifolds, is really useful for modeling geometric properties. So things like, I want to be able to model the position and orientation of the robot in space. Like that's like the most basic question we want to ask about a physical embodied agent is like, where am I? Right? Literally, where am I in space? And it turns out that like the actual set of answers that you could have to that question is actually a smooth manifold. And it's not Euclidean smooth manifold. So a way to see this, to make it concrete, would be, actually I use this example usually on the first day of class that I teach. If I were to ask you, okay, I've got a robot, let's say it's in the plane, so it's driving around like on level ground. And I might be interested in asking, okay, where is that robot right now and where is it facing? So it's the facing part of that question that sort of makes this interesting. So if you think back to like high school, if you're taking like trigonometry, and one question would be, okay, if I wanted to model the orientations of a robot, what does that look like? And you might say, okay, well, let's model it as a rotation angle. I can use an angle in the plane, and that would give me a notion. If you do that, you are going to try to assign a real number that would model this orientation angle. And so you might say, okay, well, it's just the real line, right? It's a real number line. That's what this answer looks like. That's actually not true. And it's a common mistake. And the way to see that is to say, okay, if I start in a particular orientation and I start, if I think about what happens if I think about turning this knob, maybe 0 degrees is here. And as I start to rotate, if I turn this knob up, I start rotating my robot. And that's fine until I get to 360 degrees. Because in the plane, what that means is that the robot gets back to where it started. But on the number line, I started here and I've been moving in the same direction. And so if I try to do that mapping, I end up with 2 different points that on the number line are distinct, but in terms of robot heading should be the same. So what that tells you is that what this configuration space actually looks like is intuitively, I need to take these 2 points and I need to glue them together to make them line up. And if I do that, I get a circle. So what that tells you is that actually the space of orientations in the plane is actually a circle, which, if you think back to high school, when you study trigonometry, the very first thing that you study on day 1 is the unit circle. And that's not a coincidence because that actually is what just the space of orientations looks like. So I mentioned this because, talking about manifolds and stuff may seem like a kind of very esoteric type study. But it actually turns out to be incredibly useful because these actually are the objects in question that underpin the problems that you're trying to solve. And so if you're not aware of how to handle them in the right way, you're not going to be able to write algorithms that operate reliably or that produce the correct answers. And maybe the last thing I'll say about this is just that, the mathematicians that originally developed this weren't just sort of sitting around abstrusely cooking up stuff that they could study. I mean, some of them were, but but one of the things that I think is kind of interesting about geometry is that although geometry is, can be a very abstract field, it was originally developed to solve very, very practical questions. So all the Riemannian geometers originally were actually trying to understand how can you make maps that are accurate, right? Because you're trying to represent a 3-dimensional world, which is on a sphere, on a flat piece of paper. So, what is it? What are the kinds of maps that one could write down, and what limitations might exist in terms of trying to take a curved piece of space and represent it on a flat surface, let's say. And so, even though these are can become somewhat abstract concepts, they're also kind of the natural objects that one needs to use to solve these very hard-nosed engineering questions.
That sounds super complex. Like even just hearing like the whole harkening back to high school, like I think that you were taking some much more advanced classes than I was. But no, I've noticed, even though that it seems very complex, people are interested in it, and like I was a judge for First Robotics for a number of years, and like each year it was more and more people that were joining and more kids that were interested in robotics, period. Have you seen that firsthand, like in your classes? Is that something that is accurate for people who are getting into like the more higher levels of academics?
Oh yeah, I mean, both interest actually in FIRST specifically is definitely increasing for sure. And actually, yeah, I agree with you. I sort of advised some FIRST robotics teams when I was in college for a period of time. And yeah, I mean, just the change or the advancement in terms of, number one, the capabilities, and number two, the things that we're being asked to do between like when I was in high school and when I started sort of mentoring or advising some of these groups, even over that span of like 4 or 5 years, it's gone it's gone way up in terms of, which has been really exciting actually. And as you say, like, yeah, students are coming in with a lot more exposure to these things earlier. And now actually with the development of things like robot operating systems and so on, a lot of the tool chains now have evolved to a point that actually, I mean, kind of to your point.
What is the robot operating system? Is that just like it's like DOS for like,
yeah, it's even kind of a middleware layer that allows you to sort of construct robotic systems that are meant to accomplish, whatever you want by sort of stringing together individual processing modules. So the programming sort of paradigm is that you're building a graph of interconnected nodes that perform certain kinds of operations. And so you can sort of robotic systems that will generate certain kinds of behaviors by taking these off-the-shelf individual processing nodes that do basic tasks and sort of wiring them up in the correct way to get the behavior that you want.
Yeah. That's what I was talking with another artificial intelligence thought leader on the podcast the other day, and they were saying that what's the really interesting thing that's going to happen with artificial intelligence is a lot of these much more complicated coding processes will be off-the-shelf type of apps or what have you, so that somebody who might not be as technically knowledgeable might be able to do something with it. Is that something that's accurate? Like a team of what would be done in 6 months with a team of 30 is now being done in 2 weeks with a team of 3. Is that accurate or not?
Yeah, absolutely. And so one of the big sort of things that has contributed to that, and so your ability to sort of get involved with more easily in these areas, is the proliferation of sort of software design and coding implementation libraries that have come up to support this kind of activity. So actually, maybe I should shout out to the Open Source Robotics Foundation has been a major driver in democratizing access and promoting the use of these kinds of toolkits that make this easier for people to get involved with this, that really reduce the barrier to entry.
And that's something that I feel like is only going to make those breakthroughs happen faster, right? I mean, I hope that those consumer robotics will touch a little bit sooner rather than, decades. I want them to be, just like you said, within the next 5-10 years. I want to have full self-driving. I want to have a humanoid robot that's able to do my laundry, that kind of stuff. But I also have a particularly high comfort level with robotics. I have like a lot of like that hope, inside your black box. And like, I have that outside of the black box. I'm just like, fine. Like, that's my comfort level. What's your comfort level? Because you're in the industry itself. Like, do you have a Roomba at home?
Also aficionado as well.
Right. Yeah.
I would say the main distinction between sort of like the stuff that we're targeting in my group versus sort of the broader consumer space that you're talking about is the stakes that are involved. Right? Like the worst thing that's going to happen is, your Roomba is going to chew a part of the carpet that maybe it shouldn't, right?
Right. Or bump into something that it shouldn't.
Yeah. Which is, annoying, but it's not
right. Yeah.
And so my strong suspicion is that, as we see these robotic agents start to enter the consumer market, that's the kind of thing that we'll see them get into first, right? It's stuff where, it's a great opportunity to maybe handle some stuff that would otherwise be annoying. But if the robots do, frankly, kind of dumb stuff, it's not going to be a huge deal. And so it's okay to sort of even apply, perhaps not completely reliable autonomy to those areas, right? Where you might start to maybe see a boundary, at least initially, is things like certain kinds of home assistive stuff, right? So here, I think you've given the example of like having a robot do your dishes earlier. Right?
Oh my God, laundry specifically will be a game changer. I hate doing laundry, but anyway, go ahead.
No, I do too. Yeah. So laundry might be okay. First, I sort of jump on dishes. You can imagine that if a robot makes a mistake with dishes, every time it opens the dishwasher, when you come home to, it's just like a pile of broken.
Right. Yeah. No, I think that the stakes are certainly something that's important. And I like how the Roomba has low stakes. And I feel like honestly, a lot of those low stakes things, like I would be happy with a robot that waters my plants.
Sure.
Like I would pay money for that. But on the same token, like I just don't know how far away they are in the pipeline. Right now, I see a lot of these humanoid robots and I'm like, wow, like they can walk, they can manipulate objects. I feel like everybody's talking about them and I want them to happen now. But that's just, something that as a layperson, I'm excited about. And I was wondering, how you see it coming from your angle, like how long that pipeline truly is.
So again, I think it breaks down based on, I think the question is like, what is the right application for the existing state of technology? And how can you sort of use the experience that you gain from these near term applications to improve the capabilities of these agents to then extend their capability into the future? So, things like rooms right now are a good example of this, right? Where, you can start deploying systems that are doing useful things right now. One other application that I might quickly mention that's along those lines, where I think we might actually start to see things sooner rather than later, would be things like aerial delivery. So in fact, there's one company right now that's doing amazing work that I really, really like called Zipline. And what they're doing is they're using fixed-wing drones to long-range aerial delivery of things like medical supplies in areas that don't have good like road infrastructure. So they're doing a lot of operations in Africa right now for medical supply delivery, things like that. Otherwise, it wouldn't be transportable over long distances without road networks because they have to be refrigerated. And so they're doing, I can't remember, I don't know off the top of my head what the figures are, but they're doing operations on a regular cadence right now to do like medical delivery over quite long distances, hundreds of thousands of kilometers.
So along the same vein, like I've seen the same kind of technology from DoorDash and Uber with food. Like, what's your comfort level with that? Like, would that be something that you would use, or because it's low stakes, I mean, God forbid, like, something gets lost, like it's not the end of the world, you just order another one. Is that something that you have used or you will use?
I use it myself. I would use it if it were available.
Yeah.
I mean, in fact, like I know that there's at least one. I suspect several companies are doing this right now. So I was in Berkeley a couple of years ago, and I know that there are companies right now that are doing that kind of stuff at the present because they're actually doing deployments of this. I don't know what the name of the company was.
Yeah, I think DoorDash or one of like the big delivery organizations is just coming out with it. I know Papa John's has been like talking about it for a while,
But I mean, to your point, I mean, we see like when I was out, I was seeing these all over the city.
Oh,
and,
yeah.
Like, they were like little 4 or 6 wheel, like truck looking things that were about the size of like a medium sized cooler.
Right.
They had big flags on them to make them visible.
Yeah.
And you would see them sort of like puttering along the sidewalk.
That's awesome.
Occasionally they would get stuck.
I can't wait till I see that in Kendrick Square. I mean, I feel like if anybody should have it other than, maybe Berkeley or something like that, would be someplace around here because like we're building the future just a few blocks away.
That's right.
But for whatever reason, we still haven't had that.
New England Blizzards are challenging.
Yeah, that's true. Yeah, that's probably true. Yeah, it's totally different story in California. What about full self-driving? Like, when do you think that you'll be ready for it? I feel like we've talked a lot about how the models themselves don't lend themselves to something that you're comfortable with, but
yeah, so that would be the sort of thing that I would tend to be a lot more skeptical of. And in fact, like, ironically enough, I mean, I would trust something in aviation or space well before I would trust something for autonomous driving because the environments that you're operating in are so much less complex. Like autonomous driving is actually a quite complicated problem because, like if you're flying a plane, you know how the plane works. There's not like pedestrians throwing themselves in front of your aircraft. Whereas, the amount of stuff you have to keep track of, the situational awareness that's required to be able to do self-driving well, and the kinds of like environmental changes that can happen from one moment to the next are so much richer and so much more complicated than these applications like aviation or space technology, where, you're trying to solve difficult physical problems, but in terms of understanding like what the environment and the vehicle are doing, it's just a much simpler modeling challenge than like having to keep track of what's going around you in a busy city street like in New York City, let's say.
Yeah, interesting. Do you think that any of these autonomous technologies have any influence in the capabilities of telerobotics? Like, will the autonomous stuff make telerobotics better? Will like for example, people who are missing limbs or even like exosuits like that you can use such that they feel natural. From my perspective, right now, when we talk about robots in surgery, it's really telerobotics, right? Like it's like you go in, you have this joystick and you're doing something through the lens that gives you stereoscopic vision. And it's really just a video game, right? But it takes a lot longer setup. It's still not natural, one breakthrough going to help the other? Like, is the technological progress in one thing going to affect the other thing?
I think so, yeah. Like definitely there's a direct line between like a lot of stuff we've been talking about and advances in the capabilities of teleoperated agents. But actually a great example of this that's been going on for like a decade already is actually, so like Mars is a great example of this. So I don't remember exactly what the time delay is between Earth and Mars, but I think it's, if I recall, something along the order of like 8 minutes. And so, they have these Martian rovers that are driving around doing a bunch of science on Mars. But it's actually not possible to directly teleoperate them because of the time delay between transmission and reception of information.
Yeah.
So one of the big themes that the Jet Propulsion Lab has been working on over the last several decades is how do you make these systems more capable by not having humans necessarily have to do the super low level like individual motor commands, but building up the reliability and the capability for the robot to make its own local decisions on site, and simply letting the human do more supervisory type tasks, right? So being able to say, like, I want you to go look at that rock over there, versus like, here's the exact path.
Right. Yeah, that's obviously ideal. I just don't know how much of a crossover there is. I know I could see something in that application, but when I think about robots, for whatever reason, I have to liken it back to my own experience, which is the surgical robotics component, which to me, it doesn't seem robotic at all. It just seems like a video game that they're presenting to us and using this word as a marketing gimmick, you know?
But I think you could imagine something like, suppose that you are doing surgery, and one of the things that I haven't tried this myself, but I imagine that probably one of the things that's difficult about that is maintaining situational awareness, because you're like, it sounds like what you're describing, like you're looking through kind of binocular headsets and stuff, right? So you don't have the ability to kind of easily look around and in the way that you would if you were doing.
So the thing about positional awareness in the body is that, in fact, I think that's one of the benefits of telerobotics, because the implants themselves are positioned in such a way that they're not movable. So like the implants themselves, like the actual arms of the robotics apparatus, the instruments are a known distance, and then they can be positioned on the three-dimensional CAT scan or the MRI in such a way so that you know exactly where you are from a positional standpoint, because it has this three-dimensional thing that it always knows like in what space it is. Does that make sense? Like there's markers that give you three-dimensional spatial location. So for us, I think it's something that that's actually one of the benefits of it. So even though that I'm looking through the goggle, as soon as I look up, I know exactly where I am, because it's displayed against a three-dimensional representation that has been made from imaging that has existed before this version, or before the patient was asleep.
You have to sort of take your head out of the headset and that sort of look elsewhere.
Yeah, right now, I mean, there's people that are toying around with like a lot of these AR setups, like the Apple Vision Pro and things like that, which I think there was a lot of buzz about Google Glass when they came out, being like the next big thing. So,
so that actually might be a good example. So, AR would be, I would imagine, a much more natural sort of interface than having sort of a fixed restricted field of vision. But in order to actually implement an AR interface like that, you would be having to sort of render a composite artificial view from the sensor data that your robot is collecting.
Exactly.
Which is exactly an instance of the problem that I was talking about.
Right.
So you can imagine, for instance, like, I want to use that as a basis for determining where I'm going to make decisions or things of that sort.
Yeah.
And in order to do that, I really want to know that I've got the right reconstruction so that I'm cutting where I think I am and not somewhere else.
Yeah. No, there's a lot of interesting stuff. I think that in general, technology is increasing at such a rate that, it's nice to just be a spectator. And I think that makes a lot of people very scared and very pessimistic about the future, because they don't understand what's coming down the pipeline, and people naturally fear what it is that they don't understand. But on the same token, I do think that all things being equal, we tend to go towards progress, right? I think that we're much more likely going to end up in a Star Trek scenario rather than, a Mad Max scenario. At least that's just like my understanding of it. But yeah. I don't know. I mean, I feel like artificial intelligence is this big boogeyman. The last thing I want to talk to you about is just your view of artificial general intelligence. Everybody has this idea that it's an existential threat, that it's something that they're really scared about. How do you feel about it? And if you feel, one way or another, like, what do you tell like your family members about it?
Yeah, so the way that I describe this is like, I mean, sort of in my core innately, I'm an optimist, which is why I do what I do. So I don't think that these kinds of AI systems are things that we necessarily should be afraid of. Certainly not. I mean, I think there's tremendous opportunity for them to do like actually really, really great stuff. So kind of along the lines of the stuff that we were discussing before. I mean, in terms of high level vision, what makes me really excited about the stuff that we're working on is, ultimately what these things are going to, one way that we can ultimately use them would be as assistive devices. So imagine kind of, you said before, like a car that doesn't let you crash.
Right.
Or, assistive surgical robots that don't let you make mistakes effectively, right? And I think, it's not hard to imagine how those could be tremendously valuable.
Absolutely.
On the more, I think the cautionary part of this is not that like, AGI is going to become sentient and try to like destroy like humans or something.
Yeah, like Terminator.
Yeah. I don't think that's the problem. I think the problem is much more that, if we try to deploy AI systems before they are sufficiently safe and mature, they may make bad decisions not out of malice but out of incompetence. Right? And so that's the kind of thing that I think is the contract.
Yeah.
So I don't think certainly that's not a reason we shouldn't do it.
Yeah.
All that means is just that, I think the future is very positive. We're
Yeah.
not quite there yet.
Yeah, no, I appreciate that. I think that that's one of the things that I see more so than anything is that I think that people don't realize how incompetent these machines are right now. I feel like I look at a lot of the stuff that's happening, and my sisters or some other person that's not following it thinks that like we're far more advanced than we are. Like I look at the Optimus robot from Tesla, and I'm like, that has a decade to go before it's going to be in my house. But it's nice to hear that that's how you feel too, because that's just my own opinion, and it's nice to hear it validated by somebody like yourself that's on the cutting edge. But man, this was so interesting. I feel like we really got into some deep dives, and just my understanding of robotics has been expanded exponentially just by talking to you. So I really appreciate you coming and speaking with us. We are getting close to the end of our time though, and I did want to talk with you a little bit about the general things that I ask all of my guests, which is, everything from where they gain inspiration from to other questions about the future. But specifically in that vein, where we talked about and what we both have a mutual love for is science fiction. And I'd love to hear, like, other than Star Trek, like what are some other optimistic views of the future that may have inspired you to do what you're doing right now? Because a lot of people that come onto the show, they don't even mention science fiction. So it's nice to hear from somebody like yourself that also enjoys science fiction. But there's so much dystopian science fiction. And what you mentioned was Star Trek, which is utopian science fiction, which is something that I love. And I really want other people to get involved with, because if you can see the future in such a way that it has all of this promise, I think it makes for a really different reframing of all the problems that we're experiencing now. But from that standpoint, tell me a little bit about your inspiration, where you get the inspiration to do what you do, and also some utopian science fictions that you kind of harken back to when you're in the lab and you're building the future. What do you think about?
Well, so in terms of like science fiction, I mean, Star Trek is definitely the GOAT, right? Greatest of all time.
Yeah, I mean, that vision of the future is something that we all kind of want. It's heaven on earth, like no more money, food is not an issue anymore. We're all allowed to do our own pursuits. And I think one of the best things about artificial intelligence is that it is something that can expand our life rather than take things away. I think everybody's so worried about the taking away, but I don't know. How do you feel about it?
No, I'm 100% in agreement with that. And I think, it was more specifically with respect to robots. I mean, Asimov, of course, the other sort of obvious, the other obvious answer. These are things that are ubiquitously around in daily life that are actually intentionally really trying to help us, make our lives better, right? So I think those two are sort of the obvious things that come to mind. More broadly, in terms of like, why? I mean, beyond just wanting the utopia, of course. What are some other things that I personally kind of like? I mean, I actually, with respect to like sort of intersection of mathematics and robotics, I think the reason that I really like that is because, I just like math. I like studying mathematics for its own sake, because I find it just incredibly beautiful. Yeah, the idea that like you can actually understand things about let me say this actually. Maybe here's the best way to say it. I think one of the reasons I think I like mathematics so much is that it is the only scientific discipline in which it's possible to actually get access to like capital T truth. Everything else is contingent. Right.
Yeah.
And not only that, but it's universally accessible, because all you need in order to do this is an ability to think rigorously and like a pencil to write something down.
Right.
So I like the idea that there's something really fascinating, about the fact that you can just sit in a room and just think critically about what should be true given a logical setup, and actually discover these incredibly deep, like very, very beautiful statements about the laws that govern the behavior of the universe, which is kind of incredible when you think about it. But not only that, sort of the connection between that and robotics is that, the thing that makes a robot is the ability to make independent decisions. And those are necessarily expressed at the level of like algorithms. And so to me, like a robot is really like a physical embodiment of mathematics, right? Like if you sit down in a room and come up with a new algorithm, you can put that into a machine, which is something inanimate, and make it actually seemingly come to life, right? I mean, it's the closest thing to magic that I think I've come across.
Yeah, that's amazing. I mean, I used to like math a lot in high school, but as you go through medical school, you use it less and less. And it's something that, I don't really have access to the same way that you do. Like, I feel like it provides like a framework of understanding for your daily life that it's really nice to hear. I think that, like, for example, like when I when I saw A Beautiful Mind, and this idea of like the Nash equilibrium where everybody's kind of dancing and doing their own thing. I was like, oh my God, that's like so elegant. It's so beautiful. And as somebody that doesn't use math on a daily basis, it's something that I think everybody kind of understands, right? And so that's something that I think really is interesting to hear coming from your perspective, that this is something that really frames your whole understanding. And it's not only something that needs to be only math majors that have access to it. That same kind of truth that you're talking about, it holds up whether it's somebody like me that's looking at it, or somebody that's, a layperson looking at it. So that's cool. That's cool that you're on the forefront of that, especially with something that's going to affect our life, like the way the robots are. So follow-up question to that, is where do you see this industry in 10 years? Like, are we going to have full self-driving? Is it going to be ingrained in our society the way that we all think it is? Like, are we going to have virtual assistants that we talk to more than we talk to our spouses? What do you think it's going to look like in 10 years?
Yes, I mean, like I said, predicting the future is hard.
Yeah,
but I do think, I we're really kind of hard, like at an inflection point in the deployment of robotic technology, because we are actually starting to see these things move out of the lab into like commercially available consumer products. Right?
Yeah.
So, a great example of this, folks. Well, I mean, the Roomba's one example of this.
Yeah.
A second example of this that is, I think, a little bit more technically elaborate would be like Skydio, for instance.
What is that?
Well, Skydio is a consumer drone company.
Oh, okay.
So you can actually like buy drones now that can, well, let's say very, very reliably fly around. I think originally these were originally sold as photography. So if you want to be able to like have like a drone follow you around and like take videos if you're outside doing sports or something like that. Interesting. It's able to do that. But from a technical standpoint, what's incredible about these is the level of sophistication and reliability for the onboard processing that they've achieved. So there are videos you can look online of like these Skydio drones following like mountain bikers through forests and stuff. Wow. Where they have to avoid tree limbs. Right. And they're doing all this stuff. Yeah. Trying to get the shot of this guy going. Yeah. Interesting. And they're doing all this in real time, which is an incredibly challenging, technical problem to solve, both in terms of understanding, how to get the flight software to work correctly, how to get enough situational awareness and be able to plan these maneuvers to both get the right shot while also avoiding, tree branches and, wires and thin structures and things of that sort. It's an incredible technological achievement. So in terms of just like the level of sophistication in some of the systems that are being produced now, it's very, very impressive. Yeah. Like I think drones in general are going to be much more ubiquitous than any other technology. I mean, I took my kid to this dinosaur amusement park in Atlanta the other day, and they had a drone show. And I feel like that's something that didn't really exist a decade ago. Yeah. Right. Yeah. And like the elaborate nature of like how these drones move through space, they were able to make pictures of dinosaurs and like, just like bubbles and things like that. And having seen drones, I was interested in drones for a while. Having seen them in their infancy, I know like the amount of technological progress that has happened to produce something like that. And now it's everywhere, man. Yeah. Those drone shows are everywhere. Yeah. And I feel like that's something that I see a lot, the delivery capabilities that we talked about. Who knows what else is next, but just moving it throughout space. I don't think that there's like another model that's as good as that. Even like the humanoid model, it's going to be years before they catch up to drones. Yeah. Yeah. But it's okay because like kind of, I think as roboticists, I think what's really exciting about what's happening right now is, these are sort of the first systems that have achieved a level of reliability and technical capability that actually make them economically viable as commercial or consumer products. And so just now after having, I think the earliest robots go back to like, the sort that we were describing that have to make real onboard autonomous decisions. Go back to like the 1960s, 1970s. And we've just now reached a point where our algorithmic and technical, like computational understanding and the hardware have advanced to the point where these are actually becoming not just like academic research projects, but are actually starting to get into like the real world, like actually doing like useful stuff in society. What kind of robot do you want to see in the next 10 years? What do you want to just like make your life better? And if I'm talking totally blue sky, I would love to have a humanoid in my house just doing my chores. Yeah, of course, everybody wants that. That's low hanging fruit. Okay. So the thing that gets me, you're talking about annoying tasks that I don't want to have to do. I really don't want to mow my lawn. Yeah, I just don't want to do it. Yeah. I feel like that's like such low hanging fruit for Roomba. Other than the fact that it's like up and down, I don't know. I agree. Mowing the lawn is really annoying. Yard work in general. God love anybody who's doing that.
But anyway, last question. Aside from AI, robotics, AR, VR, all of these industries that you've had direct influence on, what is something else that's coming down the technological pipeline that you just can't get enough of? That like you're reading the paper and you're like, oh, it's like this. For me, it's like longevity. That's something that I'm looking at because I feel like the idea of treating age as a disease and not in this inevitability is something that's revolutionary. But what about you? Like, what other than like the stuff that you're working in day to day, like what other technological breakthrough is like so exciting to you?
Just in general, I mean.
Yeah, just in general, blue sky.
Yeah. So the stuff that I am really excited about is things having to do with long-term sustainability and climate change. So because obviously, I mean, that's clearly a pressing question. It's probably going to be one of, if not the most important societal questions over the next century or so.
And honestly, I don't know too much about that. Like, if you're following it, like, have we made any progress at all, or is it just also an inevitability?
Well, so I mean, I think given the social importance of it, like societal impact of that. I mean, if it's not currently a top of mind priority, it's going to be necessarily becoming one in the not too distant future because we're starting to see the impact of that already in a lot of places. Like I'm from California originally, right? And the wildfire season is now there now.
Yeah, out of control, I know, right? That's crazy.
So I mean, we're seeing the effects of it right now already. And actually, I think you mentioned
Florida. Yeah,
same thing there.
Listen, I hear you, and I think that it's going to be devastating. But man, like the winters here in Boston have been pretty nice.
No, yeah, that was definitely a plus, I suppose.
Yeah, I mean, it's obviously a net negative, but from my perspective, it hasn't been uniformly negative. But like, have we made any progress at all? Like, are you following it enough to know, like, oh, okay, there's some hope down the line?
I'm going to be an expert in it myself, but sort of, following off and on. I mean, there has actually been, I think, some recent significant progress towards fusion energy, which I'm very, very excited about.
Yeah, just a few blocks away, they're making a reactor. Apparently, they made some breakthrough where now it can be made at scale, which is cool.
Yeah, I think there's actually a local company called, I know the name is Commonwealth. I think it's Commonwealth Fusion.
I think so too. Yeah.
But they're an MIT, they were a startup that I think was spun out of MIT.
Yeah.
There's actually building now like experimental plants that are like small, but like are full size, meant to be like honest to God proper fusion plants right now. So I think that's tremendously exciting.
Yeah, absolutely. The fusion stuff, I can't get enough of that. Every time I hear an article about it, even though I'm not a math guy like you are or have a physics background, I'm excited for the prospect of it.
Yeah, definitely. And so that's sort of like, so on the production side, that's one thing that I'm very excited about. The other thing I'm excited about is there's been an increasing awareness that even just being able to, that there's a great need to just even be able to understand what is going on with climate change. So in terms of like ecological monitoring, climate change monitoring, how are we going to get the data and do the data processing at the scale that is necessary to actually understand, number one, what is happening, and number two, make intelligent decisions in response to that. And so I'm sort of maybe personally a little bit more excited about that. Not that fusion, of course, is not tremendously important.
Yeah.
I just happen to be attending to that specific aspect of it a little bit more because some of the stuff that we're working on in terms of autonomy, it actually has a direct role to play there.
Right. Because even if you were to get all that data, you would need to process it. And like the breakthrough of the processing capabilities would be much more beneficial to climate change. No, I hear you. I feel like there's so much more data now than there's ever been, and that's going to be really interesting to see is like, what are the insights that are going to come once we have the artificial intelligence models to guide it or predict it or who knows what.
Yeah, and also just the fact that like even the data collection aspect of that actually really needs large scale ubiquitous autonomous systems. So I'll give you two examples. So well, one example is 70% of the Earth's surface is covered by water, right? And of course, like the ocean is a gigantic driver of the Earth's climate. Things like remote sensing don't work underwater. It's like weather satellites can't tell you what's going on with the surface. So one of the most important elements of this is an area that we struggle to be able to access. So underwater robotics, it has a tremendous role to play in terms of understanding what is going on with the oceans like just even what's going on. Yeah, literally what's going on in the ocean, and what does that tell us about climate change impacts and what we should do to correct it. Similarly, even areas that are on land, you can make remote measurements via satellite and so on. But sometimes those measurements may not be sufficient to actually tell you the full story.
Yeah.
So an example of this is I'm getting to understand from some colleagues at Northeastern and Hui that one of the big questions that climate scientists are very interested in is, how is it, like, what are the processes that drive glacial melt, let's say?
Yeah.
And so that's an interaction between ambient sunlight, the physical shape of the glacier, and air and water and ice interfaces and so on. And the level of resolution that is required in order to answer those questions is much, much, much finer than what you can get with remote sensing capabilities like, space-based weather satellites and so on.
Yeah.
And so answering those questions requires that you be able to actually place, sensors close to those interfaces in order to do that. And again, the spatial and temporal scales there are such that it has to be automated.
Absolutely. Yeah. That's interesting. Well, I hope we live in the automated future that you're talking about. I think that's something that I'm really looking forward to. I don't know if we're going to get to the level of Star Trek anytime soon, but I like how we're progressing in that direction. Thanks so much for joining us, David. Honestly, thank you all to the listeners who are enjoying this at the comfort of your own home. As always, please like and subscribe. And if you want to follow David and all this stuff that he's doing at Northeastern University and robotics, then feel free to look him up on LinkedIn and also the stuff that's located just below our video right now. Thanks, everybody. As always, I will see you in the future. Dr. Awesome signing off. Thanks again, David.
Thanks for the invitation.
Yeah. Nice speaking with you.
We appreciate you taking part in today's episode. Take this chance to reimagine a better future by joining a community of futurists who strive for a remarkable world. Be a part of this growing network and contribute to making the world a more positive place. Visit thefuturistsociety.net and subscribe to the show so you don't miss a drop of hopeful futurism.